As we look at this last topic within geometric transformations, what we're going to talk about is we're going to talk about symmetry. And we want to be able to identify reflectional, it should be reflectional, for some reason it keeps fixing itself, reflectional symmetry in geometric figures and the number of lines of symmetry, and identify the rotational symmetry and its order in geometric figures. So looking at our word, symmetry is going to be the property of having an object flipped, rotated, or moved to exactly match itself. And in doing so, a line on the plane figure that a figure can be reflected across to produce an image that maps perfectly onto itself. You know, if we fold a piece of paper onto itself in half, that line would be the line of symmetry. Or if you have rotational symmetry, it has to do with the state of being able to be rotated 180 degrees or less about a center point, and thereby produce an image that maps precisely onto the original image. Think about odd functions in algebra. They rotate about the axis at 180 degrees. They should be right back where they were. It should map to itself. And then reflectional symmetry is being able to be reflected across a line and thereby produce a image that maps precisely onto the original. And you think about the mirror reflected, so it's going to look just like the original. And the order of rotational symmetry. Did I put that? I did not, but there is going to be a order here also. And what that is the number of rotations of a figure greater than 0 and not greater than 360 degrees that produce an identical image to the original. So maybe if we had a triangle, we could rotate that and it would come back to its original self. And then let's see here. So a regular polygon is, we're going to talk about polygons too in this, and just knowing that they have congruent or they're equal angular and equilateral. So we have the same angles and same segments, sides. So looking here at symmetry, you'll notice this image of math. If we were to draw a line straight down the center of the M, we could fold it together, and this piece would overlap. You know, if we folded that way, you know, this corner maps to this corner maps to this corner, so it would fold in half. The same thing goes for your A here, your T here, and the H is unique because we can actually fold it in half that way and have it symmetric, or fold it in half this way and have it symmetric. So there's a bunch of different ways of looking at this. So as we talk again about reflectional symmetry, geometric figure is the characteristic. This is a characteristics of a figure to map onto itself across a line of symmetry. So I've taken this picture or this image of a triangle, and if we had an imaginary line of symmetry right here, we want to also identify that it is a perfect square. So if I were to say that this segment is equal to this segment, and then my line of symmetry basically is bisecting this 90-degree angle. So over here I have 45 degrees, and over here I have 45 degrees. So what I can do is I can just take this and I can flip it over to this point right here. So fold it in half, and then it's going to be sitting on itself and look something like that. And the other piece would have folded out. So that is reflectional symmetry. So as we look at it, maybe it was, as we fold it in half, something like that. And then, of course, my congruent sides are still there. Be right there, and right there would be my congruent sides. So there's just different ways to try to envision it. Rotational symmetry of a geometric figure is the characteristic where it maps onto itself across that line of symmetry, and then the lines are not lines of reflection for the triangle. Okay, so symmetry, so criteria for lines of symmetry. As we look at the last subject within geometric transformations, we're going to be talking about symmetry. So as we look at rotational symmetry, we are going to be looking at a geometric figure that maps onto itself through a center of rotation. And it's the number of rotations that map a geometric figure onto itself are called the order of rotational symmetry. So if we look here, a rotation will occur for an angle between 0 and 360, including 360. So every figure has an order that's at least 1, because it can always rotate back onto itself. So if we look here, this given figure, that this being my center of rotation, as it rotates either clockwise or counterclockwise, it's going to do, after 180 degrees, it should rotate and spin and work right back to itself. You know, as it takes and it rotates over the center of gravity, it should return to itself and cover its same position. So that is a center of rotation and moving around. So as we look at this, we have in this one also, as you think of that order, symmetry of order, that it has 2, because, well, 1 is because it will always come back to itself at 180 degrees. But if we can spin it and it rotates, and we just hit 1 rotational symmetry, and then we go back around to that 360 degrees, and we end up getting 2 rotational, or 2 order 2 of rotational symmetry. And that's really just looking at that as a general rule. We could also look at the rotational symmetry of a polygon. So as we talk about rotational symmetry of a polygon, a regular polygon when n equals sides will have order n for a rotational symmetry. So if we look at this, that has 4 sides. So we have an equilateral triangle, and thinking of n sides, so I have 360 divided by n. Well, n stands for the number of sides I have, so I have 360 degrees divided by 3, which is going to be 120 degrees for this triangle. Well, when it comes to that rotational symmetry, so at multiples of 120, we're going to have 3. So it is going to have an order of 3, and you will see that it will come back and have a mirror image, that rotational symmetry, at 120 degrees, at 240 degrees, and then at 360 degrees. So it's going to have, as it rotates, it's going to keep coming back to its symmetry, rotational symmetry. And let's see here, if we look at another example of a hexagon, and you're going to see some of these examples in your notes too. Not very good hexagon, but I am practicing. So we know that if it's a hexagon, regular polygon, all of these angles are going to be identical, and all of these sides are going to be identical. So my rotational order of rotational symmetry, well, if I have 360 degrees and I divide by n, which is my number of sides, and in this case it's going to be 6, 360 degrees divided by 6 is going to give me a 6 degrees, a 60 degree rotational symmetry, and a order of rotational symmetry of 6 because I have 6 sides. So there you go. There's some of the little characteristics. So my angle of rotational symmetry would occur at 60, 120, 180, call it 240, 300, and then 360. So what do we know about, what do we know regarding the symmetry of an isosceles triangle? Well, on an isosceles triangle, we should know that this side is equal to this side, this angle is equal to this angle, and these angles are going to be equal or congruent. And you should be able to say, well, what do we know about symmetry? Well, rotational symmetry, sure, it can be rotated all the way around to 1, or with a order of rotation of 1, because anything can be rotated 360 degrees. But this is possibly the only thing we can get here is going to be a line of symmetry. So we should, well, other than also the center rotating 360, but it should have a line of symmetry or line of reflection. So this line of reflection in blue, we would end up folding it in on itself. So we could take this corner and connect it to this corner and fold it in half, and the new image should look something like this. Something like that, the pieces being folded together, so it would be a new shape for us. So we could look at that. So we want to remember that symmetry is shown when a figure maps perfectly onto itself. We can identify the lines of reflectional symmetry as well as the angles of rotational symmetry. Regular polygons have in-fold symmetry. In-fold symmetry. So what are we talking about there? A regular polygon. So if I have a pentagon, right? 5 sides. In-fold symmetry. Well, if I were to take and fold along that line, it would have symmetry. Fold along that line, it would have symmetry. Fold along that line, it would have symmetry. So going from each one of the vertexes, you're able to find a fold symmetry. And they're also going to be regular polygons within equal sides have order n in the rotational symmetry. So here we have 5 sides. So we should have then the order 5 of rotational symmetry. So as it rotates around its center, that you would find that it maps back to itself 5 times, or every 5 times within a 360 degree rotation. Okay, so when working with these problems, if you want to find out how many sides something has or what have you, given some of the characteristics. So this is intended to be a stop sign polygon, and maybe I should try to draw it a little bit better. And a stop sign polygon is nothing more than an 8-sided polygon, which tells me that I have 8 sides and I have 8 angles. And in order to find out what those degrees are, so let's just say this, I got 8 sides. And then what are the degrees of those angles going to be? and hopefully you are able to remember that there is 360 total degrees, and as we looked before, we have 360 divided by n, and that's being the number of sides. That would give me 360 divided by 8, which is going to give me let's just do it the long way, right? 45 degrees. So each one of these is going to be 45 degrees. Let's see, so what do we know about that? If it's 45 degrees, if we know how many sides we have, we can figure out the angles. But what if they just say, okay, so separate question here. If the smallest angle of rotation for a regular polygon is 18 degrees, how many sides does that polygon have? Okay, well, what they're saying is that every 18 degrees, this thing's going to rotate right back onto itself. So here we had 8 sides. The rotational degree here was every 45 degrees, because when we divided 360 by 45, we found out that, 360 divided by 8 was 45. And so that meant every 45 degrees, it will rotate back onto itself. So what you can do is to find out how many sides does it have. Well, just take 360 degrees, divide by 18, and then you end up with 20. So that regular polygon has 20 sides for it to change those every 18 degrees. That's a pretty small little cumbersome item, actually. Now, if a regular polygon has 15 sides, okay, so we have a polygon with 15 sides. Let's see what would we say here. Is it possible what is a possible angle of rotation for that? Well, in order to figure out what my angle of rotation is going to be, what I'm going to do is I'm going to take 360 and divide it by 15. And that's going to be 2, right? 30, bring down the 6, bring down my 0, and that's going to be 4. So it looks like every 24 degrees on a 15-sided item, you're going to have that rotational symmetry, because it's going to come back to itself. So if I wanted to, I could turn around and say, well, every 24 degrees, so that's 24, 48, 72, 96, and so on, is going to find rotational symmetry based on those degrees. So really, symmetry is going to be just using a little bit of sense and, of course, applying this rule and, of course, dividing the degrees, the 360 by degrees. And with practice, you'll see that, like in most geometry, it's just sort of visual, and there's not a lot of math to it in order to get your work done.